I took the microphone off me.
Yeah. We have, I guess, the room is small enough that if you have questions, you can just go. Yes.
Michael, hear me, or what's the technology?
Oh,
Yeah.
Yes, he is online.
can you get online?
Michael, first of all, I hope you feel better. Thank you for sharing this very valuable information with our community. One question which might embarrass myself, but I really need to understand it. If you have point robots and point obstacles as your specific example, can't I just move with straight lines and with probability 1, I will arrive from start to target without colliding with the point obstacles? Thank you.
Michael.
Can I answer? Can you
Yes.
hear me?
Please go ahead.
Okay. First of all, thank you very much for giving me opportunity to present this work, and apologies that I couldn't travel. So this question, which was asked, is a very good question. In fact, what we considered in our approach is idealized situation when the sizes are small. The sizes, we assume that robots and obstacles have 0 size. So actually, topologically, it makes the problem equivalent. It still keeps it equivalent in many ways to the problem when sizes are positive. Of course, but there are differences, and of course, if the obstacles have positive size, and if they stay away from each other for a certain distance, which you can estimate, then our approach is totally equivalent, and there is no problem with that. But when obstacles may have positive size and may approach each other closely, then indeed different approach needed. And technically, it will be not a vibration. This map, which we considered, will be not a vibration, but it will have some singularities. So yes, it is a different stage of this project.
Thank you, Michael.
Welcome.
First for you.
Could you hold on just a second?
Yeah. So my question for you, I really enjoyed your talk. It was also very clear. The thing I didn't quite get is you had the red, the blue, and the yellow and the green paths in the example, and you said the blue and the red, the blue is better or lower risk, but then when you combine that with the green, it is higher risk. And I didn't get where's the change? Why is it different?
Yes.
Why is it not composable in a sense?
Yes. So basically, the idea was that between the segments, you had the correlation of collision probabilities. So if you remember that image well, there's that obstacle on the left, and the final segment, the green segment, always went close to that obstacle. So if you were, because you have to go close to that obstacle anyways, and it had that x-axis uncertainty, it wouldn't be that much marginal cost to go again kind of earlier in the trajectory. And that way, I believe it was the green one, the one around to the left, the main risk that it incurred was from that same obstacle. So even though if you looked at it just by itself, the green one that went by the left, if by itself it would have more risk than the other one, that risk was very correlated with the risk that you would see at the very end of the trajectory. Exactly. Exactly.
So Ms. Lee, so for asymptotic completeness, it was mentioned that it is asymptotically going to either return a plan or correctly state that the plan is infeasible. Is there any risk of incorrectly stating that a plan is infeasible? And if so, how is that resolved?
Right. So the definition of asymptotic completeness is that it either returns a plan or an infeasibility proof. As to the answer whether our algorithm is asymptotically complete, we have proof that the learning part will converge eventually to be an infeasibility proof. So it's up to the validation step whether it is actually a correct asymptotically complete algorithm. So then analysis of the validation step basically requires the triangulation to be iteratively smaller so that if one pass does not prove that the approximation polytope is in obstacle region, a smaller triangulation would. So that is the case with tangential dynamic complex and some other triangulation methods as well. So yes, I would like to say that our algorithm is asymptotically complete. But a rigorous proof of that definitely requires a rigorous proof of the validation step.
All right.
Yeah, so for the same paper, so have you tried in a space like SE3, and are there issues either with the dimensionality or because of its topology? And
yes, so
if I can have a second question too, are you making any assumptions about the smoothness of the obstacles so as to be able to make the proof?
There are requirements to the configuration space we need to work with. So we require the configuration space to be Euclidean, basically. We don't assume that it's a SE3 space. This is because we need to have special treatment for the boundaries of the configuration space. We treat the boundaries of the configuration space as with a thickness as part of the obstacle region. So that imagine if you have an obstacle region connecting two boundaries of a configuration space, in that case, you can still generate an infeasibility proof. So that is one requirement of the configuration space. So your second question is regarding smoothness requirement. We don't have smoothness requirement, but we do have a requirement on the obstacle region of the configuration space. That is, the obstacle region cannot be infinitesimal small. Imagine that you have like a thin piece of paper in the configuration space, then our algorithm cannot guarantee convergence to that thin piece of paper. The obstacle region needs to have some thickness so that the manifold can exist in it. So that's so all of the requirements in the paper if you want to read it.
I had a question for the first speaker as well. So